We're going to spend a little bit of time with network design and models now. Not a ton of time, not one of the larger sections in the course, but some good info here. So frankly, let's just dive right in. During your CCNA studies, the only thing you had to know about the Cisco three-layer switching model, we know the deal, memorizing the layers and their location. That was it. The stakes are a little higher here in your NP studies, as we need to know what should and should not occur at each layer. We're not going to have the same processes going on in all three layers. So we're going to do a quick review of the model. I'm going to give you a few extra details you probably didn't run into during your NA studies, and we'll hit each layer in detail as we go along. Now that core layer, switches at the core layer allow our distribution layer switches to communicate, and that is more than a full-time job. What we want to do is keep as many extra non-switch features off the core layer, with an exception or two, of course, this is networking, and let these switches do exactly what they were born and created to do, and that is switch. The core layer, that's the backbone of our entire network. So what we want is high-speed data transfer, very low latency, and I think that's enough. Now today's core switches are generally, but not always of course, the multi-layer switches we've worked with throughout this course. Now you want to be beyond careful when you're looking at your own network's requirements, looking at the documentation on the switch models. You really want to get what you need the first time. Core layer switches are generally the most powerful in your network, and they are going to need higher throughput capability than your switches found at your other layers. Now, as I mentioned, and I'm reminding you already, everything we do on a router or a switch takes away from the overall resources. So we're going to leave frame manipulation and filtering techniques to other layers. With networking, though, we have an exception, as I whispered to you earlier, and that exception is quality of service. Now, advanced QoS is generally performed at the core layer. You want to leave your ACLs and your other traffic filtering methods for other layers of this model. Now, if you are not familiar with the term quality of service, you should get familiar with it. It's not part of the CCNP curriculum right now, but basically it's a way to indicate preferred traffic, non-preferred traffic. In moments of congestion, we want this kind of traffic to go first, and we want this kind of traffic to be dropped. I am oversimplifying, but that's basically what QoS does. Now, we always want redundancy, but we want a lot of redundancy in that core layer. This is the nerve center of our entire network, can't be overstated, so fault tolerance really must be at the highest level possible. Now as for that distribution layer, not all the work is being done at the core layer. The demands on our distribution level switches is going to be high because the access layer switches will have their uplinks connecting to our distribution level switches. And so not only do the distribution level switches need high-speed ports and links, they have to have a lot of them to connect to both the access and core layer switches. The distribution layer, being the middleman, is going to be talking to switches in both layers. Again, the distribution layer switches have to be able to handle redundancy for all the links. You really want to check out your network topology and vendor documentation before buying something because, boy, in this business, it's a lot easier to get everything you need the first time around than go back and try to add it later. Now, when multi-layer switches are in use, this is where routing should occur, at the distribution layer. Because the access layer, that's too busy with end users to handle routing, and we don't want that extra routing load on the core layer switches. Now, while some QoS is going to be configured at the core layer, you will find it in the distribution layer as well. This is really our boundary for broadcast and multicast sent by access layer devices. Because if there's one thing we don't want, it's a bunch of broadcasts and multicasts hitting our core switches. We do not want that. Now, the access layer, here is where the end users finally get to communicate with the network. VLAN membership, traffic filtering, basic QoS features, they all run here. I hate to say redundancy is important here too, because it's important everywhere, but you've got a plan for future network growth. A 12-port switch might be fine what you need now. A month from now, when they add that other department they've been talking about, you're going to say, oh man, I wish I'd gotten a larger switch. A good rule of thumb for access layer switches is low cost, high switch port to user ratio. Because today's sufficient port density, as they call it, having enough ports, is tomorrow's where the am I going to put this user in that I just got. Now, collision domains are found at the access layer, and MAC address filtering can be performed there as well. Although to be frank, I hope there are other ways to get the job done that you need done, because MAC address filtering is a pain to configure, and you're talking with someone who actually likes filtering addresses and that kind of thing. So that's our look at the 3 switching layers. Now, we are going to look at what Cisco calls the Enterprise Composite Network Model. Probably going a little above and beyond the NP switch requirements, but I'd rather go above and beyond than not go far enough. And this is a good example of an enterprise network coming up on the board. Now, of course, these are guidelines. You have to use them as such. You know, that's particularly true of the Enterprise Composite Network Model. It's a very popular model to design campus networks, which is basically a series of LANs interconnected via a network backbone. Now, switch blocks are units of access layer and distribution layer devices. These layers contain both the traditional L2 switches, and if you have L2 switches, they're usually going to be at your access layer, and the multi-layer switches, which are typically found in the distribution layer. Devices in a switch block work together to bring network access to a unit of the network, such as a single building on a college campus or a business park. And we are going to have some illustrations here soon, so hang in there. Core blocks, naturally, they consist of our high-powered core switches, and these allow the switch blocks themselves to communicate. A huge responsibility. It's the major reason I'm hitting you over the head with the fact that we want the access and distribution layers to handle as many of the network services as possible, because what do we want the core switches free to do? Switch. Now, as you would expect, there is no one right way to design an enterprise network. You know, just 2 important factors, of course, the physical layout and the number of LANs involved. So anything we go over here is a helpful guideline, but still just a guideline. Now, this composite network model overall consists of 3 parts: the enterprise campus, the enterprise edge, and the service provider edge. Names of the recipes there, I think. In turn, that enterprise campus consists of these modules: the campus infrastructure, server farm, network management, and enterprise edge. Yes, again. And in turn again, the campus infrastructure model consists of these modules: building access, access layer devices, building distribution, distribution layer devices, and the campus backbone, which, as we would expect, interconnects multiple distribution models. Let's take a look at a typical campus network and see how these block types work together. There are a couple of switch blocks, LAN 1 and LAN 2. Let me slide that over. And a core block. Now, our access and distribution layer switches are both found in this model's switch block. And all 4 distribution layer switches have connections to both switches in the core block, which it gives us what? Plenty of redundancy. Now, in this situation, the core block serves as the campus backbone, and it allows switches in one switch block to talk to switches in the other switch block. Now, we love this setup, especially what we call dual core, because, you know, we never want that single point of failure, especially in a campus network. So when we have more than one core switch, we love it, because if one of them goes down, we still have total connectivity. Now, you know, reality does rear its ugly head on occasion. And that occasion may be the fact that your company can't afford a dual core or doesn't want to afford a dual core. Both of those things happen. And smaller networks can use what we call a collapsed core. And in a collapsed core, there is no dedicated core switch. Certain switches will perform as both switch block and core block switches, and it's going to look something like this. We have absolutely no dedicated core switch here at all. The 4 multi-layer switches are acting as core layer and distribution layer switches. And notice that now each of the access switches has redundant uplinks to both distribution/core switches in their switch block. Now, if you've had a career like mine, you know, there's been a time where you've wanted to take a server or 2 or 12 and just throw it out the window with little or no regard to who it might land on. But we're not going to have much of a network without our servers. And in a campus network, the server farm block is a separate switch block complete with access and distribution layer switches, as you see here. Now, this combination of access, distribution, and core layers shown here is sometimes called the campus infrastructure. Now, the distribution layer switches have redundant connections to the core switches, which we love, and this is a very small campus network. But you can already see the sheer workload the core switches are going to be handling. I mean, we got a lot of cables running to those switches, and we're not even really getting started yet. Because, of course, in today's world, there was a world once where network management tools were a luxury, and that day is long gone. We have AAA servers, we have syslog servers, we have intruder detection tools, and, of course, we have network monitoring tools, and they're found really in any campus network today. And all of these devices can be placed in a switch block of their own, which is the network management block. And that's what we've added here. Now, our core switches have even more work to do now, but we are not quite done yet, because two blocks are going to team up to bring our users that all-important internet connectivity, the Enterprise Edge block and the Service Provider Edge block. Now, and of course we had to scroll down quite a bit to even get all this on here, and you can see now we've added an Enterprise Edge block and a Service Provider Edge block. And the Enterprise Edge block, it's naturally found at the edge of the campus network. You know, it makes perfect sense. And this block of routers and switches brings WAN connectivity to the rest of the campus network. Now, while the Service Provider Edge block is considered part of the campus network model, we have no control over the actual structure of the block. Frankly, we don't even care about the actual structure of that block. We got enough to do. But the key is that this block borders the Enterprise Edge block, and it's the final piece of the internet connectivity puzzle for our campus network. And as you can see by now, got a lot of lines leading to those core blocks, right? A lot of cabling going on, and you just get an idea of the sheer workload that core switches have to handle. So that's why I was hitting you over the head earlier about, you know, we want to say routing. You know, we don't want routing done on these babies if we can get away with it. Just a quick word here about end-to-end and local VLANs. And you think, I thought we were done with VLANs. I hear you. I know what you mean. But these two VLAN types fit in with our design chat, so I just want to take a minute or two here to talk about each type. Now, as we'd expect from the name, end-to-end VLANs, what do? They span the entire network. The physical location of the user doesn't matter. A user is assigned to a single VLAN, and that VLAN remains the same no matter where the user is. Now, in today's world, just the very nature of an end-to-end VLAN and the fact that it's going to span the entire network, it makes working with one of these babies a real challenge. Now, end-to-end VLANs can come in handy as a security tool or when the hosts have similar resource requirements. Like, say, if you had certain hosts across the network that needed access to a particular network resource, but you didn't want your other host to even know that resource existed. I would keep this rule in mind. It's the end-to-end VLAN rule. They should be designed with the 80-20 rule in mind, where 80% of the local traffic stays within the local area, say the switch block, and the other 20% will actually go across the network core on the way to a non-local destination. Now, that might sound a little crazy to you already because you're thinking, okay, 80% of the local traffic stays local, and only 20% is going to leave in today's world of, the cloud and, outside the company data storage, and of course, so many things we do on the net now business-wise that we weren't doing 15 years ago. Well, you're right. Many of today's networks do not lend themselves well to an end-to-end VLAN. And what we have here is very simple. All we're doing is pointing out, where the cloud is and where the internet, across the WAN. And even this network would be difficult to configure with an end-to-end VLAN because this level of access is much more of a necessity today than a luxury. So 80-20 traffic patterns, they're getting pretty rare. And on the other side of the coin, we have local VLANs. Now they use the 20-80 rule, assuming that 20% of traffic is local in scope and the other 80% will indeed cross the network core. The physical location of the user is unimportant in end-to-end VLANs, but users are grouped by location in local VLANs. I've seen them called geographic VLANs, not very often, but I think I saw that in a Cisco PDF on their website once, stuck in my head apparently. But that's really all we're going to do with these particular VLAN types. And again, the end-to-end VLANs, the theory's nice, it's good to know for your exam, but I don't think it's something you're going to run into in the real world a great deal. That wraps up our look, frankly, at design, and let's go ahead and move to the next section. I'll see you there.